Hello and welcome to today's lecture. Very well, we are on chapter 3. We're going to start 3.2 and we talk about functions in general. For those of you who are following the e-text on Pearson, we are on page 159. Very well, so what is a function? Before talking about a function, we're going to talk about a new concept that we call a relation. Note, a point in xy plane, like A, X and Y, it includes two numbers. The first number, X, is called the first coordinate. And the second number, Y, is called the Y coordinate, or your second coordinate. For example, if I give you a point like A, 2, and 5, you can graph this point in xy plane. You have your x-axis, you have your y-axis. 2, the unit on x-axis, 1, 2, and 5 is the unit on y-axis or vertical axis. 1, 2, 3, 4, and 5. So if you connect these, the intersection is the point A with first coordinate, 2, second coordinate, 5. Very well. What if you have a collection of points in xy plane? Suppose I have A, I have another point like B, I have another point like C, D, E, and so on. If you take these points and form a collection of these points, you call it a relation. So a relation is a collection of points. We also call points ordered pairs. In xy plane. So as you can see, there is not something significant about a relation. It's just a collection of points in xy plane. It doesn't give us anything significant here. We're going to use a relation or a collection of points in xy plane and define something that we call a function. A function is a relation. It means that a function includes some points in xy plane with this specific condition, such that for every x value, we can assign one y value. That's the official definition of a function. So a function is nothing but a relation, a bunch of points in xy plane, such that if you take any x on x-axis, there is exactly one y value on y-axis associated to that x. Consider this example. The following relation is a function. So what is the relation? We have a collection of these points, -1, -2, and -1. Then you have -1 and 1. Then you have 0 and 3. You also have 1 and 5. And you have 2 and 7. This set or this collection is a relation. Why is that? It's just a bunch of points in xy plane. The first point, the second point, the third point, the fourth, and the fifth point in this collection. This is a relation. So we're going to make sure this is a function as well. To each x value, like -2, you assign one y value. To each x value, -1, you assign one y value, which is different from the previous one. For each x value, you have specifically one y value. If your x is 1, your y is 5, which is different from the rest of the y's. To each x, 2, you assign just and exactly one y value, which is, in this case, 7. So we say that, hey, let us take all first coordinates and form a new set, which we call the domain of the function. So domain of the function includes all first coordinates, -2, -1, 0, 1, and 2. We also have a name for the collection of all y values. We call it the range of the function. -1, 1, 3, 5, and 7. Well, one way to graph this function is to use the set of elements in the domain and use the set of elements in the range and use some arrows to connect them together. So for our function here, the collection of domain values can be listed here. -2, -1, 0, 1, and 2. And the collection of range values are going to be on the right-hand side. You have -1, 1, 3, 5, and 7. So now we're going to connect each x value to its y value. -1, -2, and -1. So you connect them with an arrow. -1 to 1, you connect these two with an arrow. 0 is connected to 3, 1 is connected to 5, and 2 is connected to 7, sorry. So in this case, you say that your x values are free variables or they are independent variables. Free or independent. And values, y values in your range are all depend on your x values or independent values. So you call them dependent. This is one of the methods to visualize and graph your function. So we are on page 160. So as you can see, for a function, you have a collection of ordered pairs, and when you graph these points in xy plane, no vertical line crosses 2 points or more at the same time. We call it vertical line test. Note that a relation is a function if its graph passes vertical line test. It means that if you take any random vertical line, there are no more than 2 or 3 or 4 intersections of that vertical line with those points. So at most 1 point. It means that any vertical line has at most 1 intersection with points in the graph. So think about this as any random vertical line. Just note that that vertical line must be somehow intersecting the points in the collection of points in your relation. So what do I mean by that? Take a look at these 2 examples. The first relation and the second relation. Your first relation has some points. The first point. The second point, let's call them A, B, C, D. And your second relation has point A, point B, and C, and point D. These 2, of course, are relations. Those are including some points in xy plane. So let's begin by checking vertical line test for the first relation. I'm going to take any random vertical line. So it doesn't make sense to take the random vertical line here. That vertical line somehow needs to have intersection with points in xy plane. So let us move this vertical line, for example, here. That vertical line is intersecting 1 point at a time. So this relation passes vertical line test, and this relation is a function. Since it passes vertical line test, this relation is a function. How about this one? So let's take a random vertical line and see how many intersections do we have here. Unfortunately, for this relation, this vertical line, random vertical line, has more than 1 intersection. This vertical line has intersection with point C and D at the same time. So this graph, this relation, doesn't pass vertical line test. So we say that it is not a function. Since it does not pass vertical line test, it is not a function. On page 161, we have some more graphs, and we can check vertical line test for each of these graphs. Very well. Example. Which one is a function? So suppose you have the following graphs. The first graph is like this. The second graph is actually a parabola. And finally, you have a circle. So which one representing a function? All of these are relations. If they pass vertical line test, we say that that graph represents the graph of a function. For the first one, if you take any random vertical line, it has at most one intersection with the graph, and of course, it is a function. How about this parabola? If I take any random vertical line, it has at most one intersection with the graph of the function, and this is a function. Here you have a circle. There is a relation, and it is a circle. Let us take a random vertical line. As you can see, it has more than one intersection with the graph of the relation here, and it is not a function. Well, now suppose you have some graphs, and you know that you have graph of function, and you want to find the domain and range of that function. So suppose you have this example here. Find the domain and range of the following function. So what's given in this case, part A, you have a linear function. So this is your x-axis, and this is your y-axis, and the graph is given this way. This is a linear graph. It continues both sides, from left, from right. It continues. We don't have any formula for this line, but we know that the domain of the function or domain of the relation is x values. So x values. If I project this line on x-axis, the projection of this line on x-axis, it gives me all x values that belong to the domain of this line. So if you shade all of these values, it has negative infinity to positive infinity as its domain. So the domain is negative infinity to positive infinity. You can leave it in interval form, or since negative infinity to positive infinity is all real numbers, you can represent that by R real numbers, or you can use set notation, the set of all x values such that x is a real number. How about the range of the function? The range of the function, remember, we define the range to be all y values. So instead of working on x values, x-axis, we're going to project this line on y-axis. Very well. Let me see if I have a different color. So let us take this line and project it on y-axis. So I'm projecting my line onto y-axis to find my range. So this line continues. I have to continue projecting the rest of it on y-axis. For the part on the left-hand side of y-axis, if I take these and project them on y-axis, and since it continues, this projection continues. And if you shade y-axis, you can find your range, which is again negative infinity to positive infinity. In this special case, since you have a line, the domain and range are the same. Both of them are real line. Now, the set notation, you have to use a different variable. X is for x-axis, y is for y-axis for your range. Instead of all y values, such that y is a real number. Another example for you. Suppose this graph is given. X-axis, y-axis. So suppose this graph is given like this. And this is 1, and this is 1 and 1, and at 4. Suppose this is 3. What's the domain of this function here? Note that this passes vertical line test, so for sure you can say that it is a function. To find the domain, we're going to project this graph on x-axis. So the projection of this point is going to be that point. We're projecting the rest of the curve, the graph of the function on x-axis. Continue this process. And for the last point here, you see there is a hole in the graph of this function. So if you project this point, you're going to have a hole at 4. So the domain of the function is all points between 1 and 4. 4 is not included. Note that 1 belongs to the domain of this function. So how do we write this down mathematically? The domain is half closed, half open interval. So we use bracket to show that this point belongs to the domain 1, comma, and it includes all of these points except the endpoint 4. So we use parentheses to show that that point doesn't belong to this domain. We can also use set notation, the set of all x values such that x is in between 4 and 1 is included. How about the range of the function? Of course, we have to project the graph on y-axis. If you project this point on y, it starts at 0. The projection, we're projecting the graph on y-axis. And note that the end point is a hole. So, as you guessed, 3 is not in this range. 0 to 3. So the range of the function is 0. It starts at 0 and stops at 3. 0 to 3. Or you can represent this. Note that for y-axis we use a different variable y such that y is in between 0 and 3 is not included here. Let us take a look at our book. On page 163, there are some examples for you. The first example is y equals to x, which is a line passing through the origin. Since it passes vertical line test, it is a function. The domain of the function is negative infinity to positive infinity, and the range of the function is negative infinity to positive infinity. Suppose you have another line. Since the slope is negative, you have a decreasing line. It passes vertical line test. It is a function. The domain of the function starts from negative infinity and it continues to positive infinity. So the symbol that we're using is parentheses negative infinity to positive infinity. Also for the range of the function, as you project this graph on y-axis, it starts from negative infinity and it continues to positive infinity. Suppose you have y equals to x squared minus 4. In this case, you have a parabola which opens up. It passes vertical line test, so you have a function. The domain of the function. If you projected the graph on x-axis, since the graph continues to both sides, the projection on x-axis starts from negative infinity, and if you project the rest of the graph on x-axis, it includes the line segment here. And also, if you project the right-hand side on x-axis, it goes to positive infinity. So domain, negative infinity to positive infinity. How about the range of the function? We have to project the graph on y-axis. If you project the graph on y-axis, as you can see, it starts at -4. And as the graph continues on both sides, the projection on y-axis continues to positive infinity. So we're using a bracket, -4, because this point belongs to the graph of the function. So bracket -4 to positive infinity. Also for y equals to absolute value of x. Absolute value function has a V shape. Is this a function? Of course. Since the graph passes vertical line test, it is a function. The domain, the function continues to both sides. The projection of the graph on x-axis on both sides covers all numbers on x-axis. So you have negative infinity to positive infinity. How about your range? We project the graph on y-axis, and as you can see, it starts from the origin, 0, which belongs to the graph of the function, and it continues to positive infinity. How about reciprocal function? Y equals to 1 over x. The name of this function is reciprocal function. The graph of the function, as you can see, is like this with two separate parts. First of all, this is a function. It passes vertical line test. How about the domain of the function? When it comes to the domain of the function, since the graph has two portions, two subgraphs, the domain can be written as the union of two intervals. Let us discuss the left-hand side graph. The projection of left-hand side on x-axis, as you can see, this graph continues to the left side. So it starts from -infinity and it stops at the origin, but since the graph never touches y-axis, there is no way you can include the origin on x-axis. So that's why we use parentheses for 0. How about right-hand side? If you project right-hand side on x-axis, you see the graph never touches y-axis. It means that there is no intersection between the graph and y-axis. So if you project this endpoint on x-axis, it doesn't include the origin. That's why we use parentheses 0. And for the rest of the projections, it goes to positive infinity. Sorry, we are here. The same for the range of the function. If you project the graph on y-axis, it starts from -infinity and it stops at the origin. But again, since the graph never touches x-axis, the projection on y-axis never includes 0, union with the second part of the graph on top of x-axis. So if you project this graph on y-axis, again, since the right-hand side never touches x-axis, your y value never starts at 0 included. So you have to exclude 0 or the origin from the range of the function. And as you can see, it continues to positive infinity. So you have to include infinity for your range. Well, let us move on to the next page and talk about a function in general and how to evaluate a function. So, in general, you can represent a function as a machine like f that takes on values for x, makes some changes to those x values, and it gives you back some numbers, some values like y. So y can be represented using f of x. In general, if you have a function, you can either use y equals to that function or f of x equals to that function. Y equals to the function, whatever the function is, the linear function, it's the constant function, it's a quadratic function, and so on. Or you can write it as f of x equals to that function. It usually easier to use f of x equals to that function when you want to evaluate the function. Let me go over some examples to illustrate this here. For example, the first one, it says, let f of x be defined as 3x plus 2. The question says, evaluate the function when x is equal to 1. So what's the meaning of that? It means that when you see this function, wherever you have x, just substitute that with 1. Okay, I have this function here. I have f of 1 equals to, I have 3 times 1 plus 2. So I'm not making any changes to f of 1. I'm just calculating this number here. 3 times 1 is 3 plus 2 is 5. So f takes 1, it changes 1, and it gives you back 5. What's the meaning of that? It means that when x is equal to 1, your y is equal to 5. So you have the first point on the graph of the function. So it means that the point 1 and 5 is on the graph of the function. Another example for you. So let f of x be minus 4x squared plus 3x minus 2. And question says evaluate the function at 2 and at negative 1. And at x equals to negative 1. So in this case, this question gives you 2x values and it asks you to evaluate the function at these 2x values. What's the meaning of that? The question is asking to find your y value. Very well. So wherever we see x, we just substitute that with 2. Wherever we see x, we substitute that with minus 1. So let's calculate each of these separately. So f of 2 is equal to minus 4, 2 squared plus 3 times 2 minus 2. And f of minus 1 is equal to minus 4 minus 1 squared plus 3 times negative 1 minus 2. We're going to calculate each of these separately to find 2y values. So this is equal to minus 4 times 4 plus 6 minus 2, negative 16 plus 4, which is negative 12. It means that point 2 and negative 12 is on the graph of the function. What about this one? Let's do the calculation. We have negative 4 times 1 minus 3 minus 2, or negative 4 minus 5, or negative 9. The point negative 1 and negative 9 is also on the graph of the function.